in the collection of papers, number 11. I want you to read it. The authors, I believe, are Snyder, Grushka, and Knox. And it's an old paper, really old, but it's really good. And what they do in this paper is they take a number of different models of band broadening, different approaches to calculating what the band broadening will be, and compare them to one another. And I think by comparing them, you'll pick up a lot of the nuances of the different models. When you read this paper, what I want you to do is think about what are the good things about each of the four models. There's four different models that they discuss. And what are the deficits of those models? What do they do? What do they not do for you? So this is a critical read. The paper is not mathematically heavy like the Sternberg chapter was, and it's not as long by quite a margin. It's like 10 pages long, and it's, I believe, a very clearly written paper. But it's a very good paper to get into. Then, in the notes called Dynamics A, which we did last week, I want you to do problems 1 through 8, or there are only 8, to do all the problems there. They're actually not difficult problems. One of them involves doing least squares analysis of some data. You're going to need to use Excel. I assume you all have Excel and know how to use Excel. You're going to need the regression tool in the Excel spreadsheet to analyze the data. And very likely there'll be a quiz on Wednesday. Okay, so that's the late-breaking news. Now today we're going to get into the Giddings random walk model of peak broadening. In fact, we started it on Friday. But what we're going to do today is actually apply it to the different broadening factors in the Van Deemter equation, and we're going to actually calculate the values of the broadening factors. So first, we're going to take on the easiest one to deal with is the so-called longitudinal diffusion term, the B term. This represents the broadening that comes about due to molecular diffusion along the axis of the column. This is what we call longitudinal diffusion. And this process takes place in the mobile phase, and it also takes place in the stationary phase. They happen independently. So first we'll deal with the mobile phase, longitudinal broadening, B term, and then we'll do the stationary phase, longitudinal broadening, B term. We'll add them together. We'll get the total B term by adding them together. So that one's the easiest to deal with. We'll start with that one. Then we're going to deal with the slow interphase mass transfer contribution, the C term contribution. That's the next simplest one to deal with in terms of this particular model. And the last one we're going to deal with is the Eddy dispersion term, the A term, the broadening that results from the fact that the velocities of the molecules in different flow streams are not all the same. And this is what we call Eddy dispersion. It turns out that there are 3 subcases, if you will, of this A term. The first we'll deal with is what Van Deemter did. This is what's called the classical A term. And it works to a certain extent. Remember that the A term is the velocity-independent contribution to the peak broadening. It was discovered that Van Deemter equation is not always absolutely correct. and that sometimes it looks like this contribution is velocity dependent. So a few years after the Van Deemter equation was put out, some other people came along and said, we don't agree with all of the assumptions that Van Deemter and his crew made, and we believe that there's a substantial, if not dominant, diffusional contribution to eddy dispersion. And so there was a second approach developed, second subcase, if you will. And then a few years after that, Giddings said, well, you know, I really think they're both wrong. And he came up with a third approach, which actually is a very general approach that says Van Deemter approach and the diffusion approach are actually coupled together. They're mixed together. And this is what we call the Giddings coupling form of the eddy dispersion equation. And I'll show you today, I hope, how the random walk model actually treats all three of these subcases. So, here are the equations I showed you the other day, the basic equations of the random walk. The two key equations are the Einstein equation for the variance of the peak. And Einstein said the variance of the peak is equal to the number of random steps that the particle that's diffusing, or the particles that are diffusing take, that's n, times the square of the random step size, that's L. So if you can estimate n by some concepts and L by some concepts, you put them together and you get sigma. You get the variance. It's one way to do the problem. Another way to do the problem is if you have the equivalent diffusion coefficient and you know the period of time that that kind of diffusion is taking place, then you can estimate the variance as 2 times d times t. This is the equation for the peak variance that comes out of solving fixed laws of diffusion that we did last time. No, the time before last. We'll also need this third equation that says if we have more than one source of broadening, one source of peak variance, then the total variance is the unweighted sum of the individual variances. And if we have n, then it's the sum of all n variances. And I say unweighted, the weighting coefficient is 1. They're all equally weighted. The HETP, coming from basic stuff, is the variance of the peak divided by the length of the column. And so since this is true, this is true, and this is true, we put them together, and we see that the total HETP is the sum of the variances divided by L. We add up the individual variances. So if we have a variance due to the A term, the variance due to the B term, the variance due to the C term, we can convert those to individual HETP contributions, add them all up, unweighted. That's the total HETP. So we're going to use these equations and develop them in the context of the random walk model. Okay, so let's start talking about longitudinal diffusion. So what we're talking about is, here's our column, and we have a bunch of molecules inside the column, and they're in there for a certain period of time, and they're undergoing diffusion, which means they're moving randomly in the direction of the length of the column. So they're diffusing along the axis of the column. The width, the sigma of the zone of solutes, if we have their diffusion coefficient, and if we know the amount of time that they're undergoing diffusion, then we can calculate the zone, the sigma of the zone. We take the sigma of the zone and convert it to an HETP by taking the sigma squared, divide by L. That's the HETP for this process. So let's think about the process of diffusion in the mobile phase. So the first thing we need to do is come up with an estimate of the mobile phase, the effective mobile phase diffusion coefficient. That's this number. Now, diffusion in the mobile phase inside of a column is not exactly the same as diffusion in a beaker, where there's no particles of stationary phase. You've got particles inside the column. Now these are not molecules, these are particles. Here's a molecule in the mobile phase. Well, this molecule, its ability to diffuse, is screwed up by the presence of those particles. These molecules of solute are going to bang into those particles, if you will. And that's going to slow them down. It's going to make diffusion slower. And that's what this factor is called, this gamma sub m. It has a lot of different names. Some people call it the obstruction factor. Some people call it the tortuosity factor. Some people call it the labyrinth factor, like walking through a labyrinth. There have been attempts to model this by computer experiments, but basically it can be measured experimentally by packing a column and making the measurement. And it turns out that this factor is more or less always between about 0.6 and 0.7. Obviously, it has to be less than 1 because this can only slow diffusion down. So typically, this number is 0.6 to 0.7. So now we have our first number. We're going to stick that in there for the diffusion coefficient in the mobile phase. D sub m is the diffusion coefficient of the molecule in exactly the same liquid that you have for your mobile phase, but there's no particles around to mess up its diffusion coefficient. The other thing we have to come up with is an estimate of T, the amount of time that the molecule's undergoing diffusion. Well, this is really easy to come up with. The time that a molecule spends in the mobile phase is equal to the length of the column divided by the average velocity that the molecule has when it's in the mobile phase. Now, this is not the same as the zone velocity. The zone velocity is different because the zone velocity accounts for how much time, what fraction of the time the molecule spends in the stationary phase. Well, the time it spends in the stationary phase is not undergoing diffusion in the mobile phase, it's undergoing diffusion in the stationary phase. U sub e is the average velocity of the mobile phase when it's moving around the particles. It's the interstitial velocity. So all molecules, regardless of how much they may be retained, spend the same amount of time in the moving phase. So we put this time in there, into the equation for T, and we calculate sigma. So sigma is 2 times gamma times d sub m times L over the velocity, the interstitial velocity. You see the inverse dependence on the velocity. So this is the B term in the Van Deemter equation. Now we calculate the HETP by taking sigma squared and dividing it by L. So if we do that, divide by L, that L goes away. And so this is the HETP from longitudinal, or also called axial, molecular diffusion in the mobile phase, in the mobile phase, in the mobile phase. Now we also have to worry to a certain extent about diffusion in the stationary phase. Now I agree that most of the time the diffusion in the stationary phase is going to be a slower process than diffusion in the mobile phase. But you also have to think of the fact that molecules tend to, if they're strongly retained, they're going to spend a lot more time in the stationary phase than they will in the mobile phase. And the time that a molecule spends in the stationary phase is equal to the time that it spends in the mobile phase times the retention factor, K prime. If the retention factor is 0, it never goes in the stationary phase. It doesn't spend any time in the stationary phase. There's no diffusion in the stationary phase. But the more and more and more and more it's retained, the more time the solute spends in the stationary phase, the longer the time it has to diffuse in the stationary phase. I'm going to combine a whole bunch of algebraic steps, but they're trivial. I just showed you what they look like for the mobile phase. If we put it together, we get 2 times the obstruction factor for diffusion in the stationary phase particle times the diffusion coefficient of the solute in the stationary phase liquid. So imagine you had a beaker full of stationary phase liquid. If it were a polymeric stationary phase like we use in GC, it would be the gooey polymeric liquid, and diffusion in it might be quite slow. And we have our retention factor, and we then have our inverse dependence on velocity, because L over UE is T sub m. L over, then we'll convert the sigma squared to an H. We take sigma squared, divide by L, so that L has been divided out, so to speak. And it's still an inverse dependence on the velocity, so it's still a B term. What the B term really is the sum of the longitudinal diffusion in the mobile phase and the longitudinal diffusion in the stationary phase. So there's the mobile phase part, there's the stationary phase part, and there's the inverse dependence on the velocity. So this is the whole B over U sub E. And that's it. 2 parts. Now, in gas chromatography, the mobile phase is a gas, obviously. The stationary phase in gas chromatography is typically a polymeric liquid. Now, the difference, the ratio of diffusion coefficients in gases to liquids is immense. 10 to the 3, 10 to the 4. If it was a polymeric liquid, it could be 10 to the 5 or 10 to the 6. This term in gas chromatography is generally not very important, even if you've got something that's really well retained as K prime at 10. chromatography with a K prime of 10,000. It's just not going to happen. Take too long for it to come out. So this term is usually negligible in GC. But in LC, the mobile phase is a liquid and the stationary phase is liquid-like, and so you can't say one is necessarily a lot different than the other. And in LC, we have to deal with both of these processes. In supercritical fluid chromatography, where the mobile phase is a supercritical fluid, which is a denser gas, if you will, diffusion in supercritical fluids is slower than in gases, but it's usually a lot faster than in liquids. So it's frequently the case that the second term in supercritical fluids is not very important. In capillary electrophoresis, we have no stationary phase. It's not there. So the second term here is gone. But you still have to deal with the fact that the molecule can diffuse when it's in the moving electrophoresing media. So this term is present in electrophoresis, whether you like it or not. Okay, so that's the B term. And you saw how nice it was because we could use the simple fixed law problem. But the next two things we're going to deal with, the C term and the Eddy dispersion term, we're going to have to use the Einstein estimate of the variance. We're going to need to come up with estimates of the number of random steps and the size of the random step. And this is where we have to be very careful in our analysis of the problem. And just to remind you, I went through this slide a couple of days ago. This is why the slow transfer between phases, the interphase transfer process, causes broadening. And this sort of explains why it shows up as C times U, is that the solute in the stationary phase has to keep up with, has to stay in equilibrium with the solute in the mobile phase. And the faster we move the stuff in the mobile phase, the further away from equilibrium is the situation. And so the worse the peak shape, the worse the peak broadening. This is another way to talk about that same problem. I sort of like this picture. So here's your analyte molecule, and it's in the moving phase. And when it's in the moving phase, it's subject to axial transport by convection. Because the fluid, the moving phase, is moving, it's being transported. And it's being transported down the column by the flow of the mobile phase. If you want, you can think of the solute as being pushed down the column by the moving fluid phase, be it a gas or a liquid or a supercritical fluid. But the solute, in order to undergo chromatography, has to move laterally, perpendicularly to the axial direction in order to become equilibrated with the stationary phase. So it wants to achieve this equilibrium condition. You can view this as an absorption coefficient here and a desorption coefficient, or you can think of it as a forward rate constant and a backward rate constant. And when Giddings developed this particular problem, he called it KF and KB. And so if you go to Giddings' book, I wanted to use the same symbols that he used so you could follow the book if you went there. So I'm calling this step where the solute leaves the stationary phase and gets into the mobile phase, I'm calling that KF, the forwards motion. And this is the backward rate constant. They're regular chemical rate constants, first order chemical rate constants. They have units of inverse time. Now, it should be clear that if these two processes here are slow compared to this process, you're going to get peak broadening. And the faster you do this process, the more broadening you're going to get. So clearly, if you increase the velocity of the solute when it's in the mobile phase, you're going to make broadening worse. What's going to be important to us in working this problem is, what is the time scale of these processes, the forward and the reverse process, the forward and the backward process, relative to the time scale of the axial transport. So we're going to have to convert these rate constants into time factors. And the way we usually do that in chemistry for a first order process, not a second order process, but a first order process, is the corresponding times would just be taken as the inverse of the rate constants. So if this rate constant has units of inverse time, then this is time. Same here. If it has inverse time, say inverse seconds, then this is in seconds. So TF would be the average time for taking that step. And TB would be the average time for taking that step. Okay, now, we're going to have to use this equation, the Einstein equation, so we've got to estimate N, and we've got to estimate L. By the way, this is going to come in handy. This is just like the other day when we talking about adsorption and desorption. K prime is the ratio of the rate constants. So we got Kf and Kb. Okay. Now here's the first argument of the model. We need N. N is the total number of random steps taken. Well, there are two parts to that. There's the number of backward steps and there's the number of forward steps. Now, in order for a molecule to get from the top of the column to the bottom of the column, the number of adsorptions has to equal the number of desorptions. If the number of adsorptions is greater than the number of desorptions, it's not going to come out. So if NB equals NF, then N is equal to NB plus NF, and NB equals NF. So N is equal to the sum, and N over 2 is equal to NB, or is equal to NF. So we can get this, as soon as we can estimate that or that, we have N. Okay, I just said that. Now let's consider TF, the average time spent in the mobile phase per step. Well, if NF is the total number of forward steps, and U sub E is the velocity of the solute when it's in the moving phase, and TF is the time that it spends per step in the moving phase, then the product of N times U times T has got to be the length of the column. Because in each individual step, it will move forward by U times T sub T. And if it does that NF times, it's boom, 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 and it's out of the column. NF is equal to L divided by UE times TF. And then N is equal to 2L over UV times TF. So now I have N. I now need to estimate L. Okay, now, we have to be very careful about how we conceive of L. L is actually the size of the step relative to the center, relative to the zone position. So we need to know the average velocity of the zone of solutes. We need to know the average molecule's velocity, and that average molecule velocity is equal to U sub E, the velocity when it's in the moving phase, divided by 1 plus K prime. Let me put it another way. Molecules are either moving or they're stationary. That's it, right? The fraction of the molecules that is in the moving phase is 1 over 1 plus K prime. We did that like day 2. The velocity of the molecules when it's in a stationary phase is 0. So we don't need to know the fraction of the molecules in the stationary phase. So if we take the velocity when it's in the mobile phase and multiply that by the fraction of the molecules in the mobile phase, that's got to be the average velocity. That's what this is. Now, how big of a step forward does a molecule make when it's in the moving phase? Well, it's a step forward relative to the average position of the other molecules. So the step is TF, the time in the mobile phase, times the difference between the velocity when it's in the mobile phase and the average zone velocity. And this difference in velocities just works out to be UE times K prime over 1 plus K prime. So now we have L and we have N. So we're going to get sigma squared by plugging in N and plugging in L. So H is sigma squared over L. Sigma squared is N times L squared. So we're gonna put this in for L squared. Sorry, I've got to go back. We're going to put this in for N. And do my algebra. So the HETP turns out to be 2 times the velocity in the interstitial space times time, the time per step forward, K prime plus 1 per K prime squared. But by algebra, that would also be equal to 2 UE TB K prime times 1 plus K prime squared. This K is not squared. And all I'm saying is that TF equals TB over K prime, which is back a slide or 2. Now what I got to do is estimate the time per backward step. But that's 1 over KB. So TB equals 1 over KB. Put that in. And I get HETP equals 2 times UE over KB, K prime over 1 plus K prime squared. This is exactly what that god-awful first-order Bessel function, modified first-order Bessel function gave as the result for sigma squared when we converted sigma squared to h. Without doing any of that mathematics, just a little algebra and a little thinking. It's not a coincidence that this is exactly the same. So this is your C term. And you can see that if we increase the velocity, the h gets bigger, more broadening. If we decrease the rate constant, the h gets bigger, more broadening. And it's k prime dependent. If k prime is 0 and there's no retention at all, it's never going to move from the mobile phase to the stationary phase. Doesn't matter how fast or slow it does it. If it never goes, it never goes. It can't cause broadening. So that's B and C. Now the Eddy dispersion process is the final thing, and we'll first work the problem so that we use some of the ideas that Van Deemter and his crew used, but this is basically, we're going to be applying the Giddings ideas of a random walk model to do it. But first I want to make sure that we understand the physics of what we're talking about. So here's an attempt to draw in 2 dimensions the structure of a 3-dimensional bed. And the solid lines with arrows are supposed to represent different flow streams. That is, different ways in which the fluid can move through this bed packed with particles. And you'll notice that the flow streams don't always just move straight down the tube, down the column. The fluid is going to have to be diverted as it hits a particle. It's going to have to flow around the particle, so that there are components of velocity which are in the direction of the exit of the column, but there's components of the velocity that move also laterally. What that means is that they cause mixing. Now, the different flow streams, like the flow stream up here, and the flow stream there, and the flow stream here, even though more or less in the same direction, do not necessarily have the same velocity. Because some of the channels are going to be wider than other channels. Okay? So we have quite a dispersion, if you will, in velocities. And by velocities, I mean the velocities that way, down the column. Now, if we have different velocities down the column, then molecules in different flow streams are going to be transported through the column and get out quicker or slower than molecules in a flow stream that has the average velocity. And that's going to cause dispersion in the peak at that end of the column. That's what we're talking about now. That's what eddy dispersion is about, of the zone as it moves down the column, because the axial velocity is not the same everywhere in the column. If it were, the molecules would move through the column lockstep, and there wouldn't be any broadening. Another way to think of it, this is the more regular array of particles, but between each couple of particles there's a little tiny mixing chamber. You think of little propellers in there causing stuff to mix up. And the longer a molecule spends in the mixing chamber, the wider the peak is going to get. Another way to conceive of the problem is what people call the capillary model of the packed bed. Instead of thinking of the bed being packed with particles, imagine the inside of the bed is got tiny tubes, and the molecules are moving inside these itty-bitty tubes, and the tubes are all lined. But the velocity in the tubes are different because the tubes are wider or narrower. So if they have different velocities, then when they get out the end of the column, they're going to come out at different times. But that's an unrealistic model because it really is packed with particles. So you have to imagine that the tubes are randomly connected to one another so that material can exchange between the different tubes, either by diffusion or by convection. Again, you can have transport, you can have lateral transport, that's the lateral direction. You can have lateral transport because some of the flow streams actually go laterally. Or you can have transport by diffusion laterally. Now Giddings, when he thought about this eddy dispersion process, he said, you know, it really is a lot more complicated than what Van Deemter thought, in that there's lots of different sources of inequality in axial velocities. So what I want you to think about is this top picture here. This is the inside of a column, and you could think of this as the positive and the negative radial position. And right here is the center of the column. That would be R equal to 0. And that the flow direction is that way. And Giddings analyzed this, and he said, you know, I see 5 different velocity domains or regimes in this column. The worst case is we can have velocity differences that extend over the entire diameter of the column. He calls this a trans-column, a cross-column velocity difference. What he's saying is the following. He's saying that the velocity in the center of the packed bed is different than the velocity at the walls of the packed bed. There's a number of reasons why this might happen, but the biggest reason this thing will happen is that the wall of the column screws up how the particles can pack in the immediate region of the wall. And in fact, the density of particles is lower in the wall region than it is right in the middle of the packed bed. He then talks about these other types of velocity inequalities. We have a channel here on this scale, and that the fluid flow everywhere inside this channel is not the same. The fluid right at the particle boundary is stagnated. The fluid right in the middle of the channel is moving faster. And so on and so on and so on. And he says there are 5 different kinds of this process. I'm not sure I buy this 100%. I'll go maybe 70%, maybe 80%. And it doesn't really matter too much that you buy that there are 5 different kinds of velocity, sources of velocity inequality. But you've got to buy the fact that there are differences in velocity depending on where you are inside the column. And that's all we need to deal with right now. Okay, so again, we're going to estimate the variance by knowing the number of steps and the step size. But this is a different process than slow interphase mass transfer, and we have to come up with different estimates of these parameters. Okay. The first point is the following: that the axial velocity everywhere in the column is proportional to the average velocity. That's the average interstitial velocity. So what he's saying is we got a bed packed with particles. Let me look at one particular position in the column. If I double the average velocity, I'm going to double the velocity at that specific position in the column. If I halve the average velocity, I'm going to halve the velocity at that specific point in the column. So, if you will, the column behaves in proportion to the average velocity. So the difference in velocity of a molecule at some point z relative to the average, since this is proportional to the average and this is the average, then the difference in velocity relative to the average is going to be some proportionality constant, omega. And Giddings puts the subscript beta on it. And because he believes there are 5 different kinds of velocity inequalities, beta can be 1, 2, 3, or 4, or 5. But the point is that the difference in velocity relative to the average mobile phase velocity is proportional to the average mobile phase velocity. The step size relative to the average, therefore, is going to be equal to this proportionality constant times the average velocity times the time that it takes a molecule, this is key, this is the time that it spends in that flow stream to get from that flow stream to the average flow stream. So this is the transport time, that's why it's T sub T, the transport time to get from flow stream of type beta to the average velocity regime. And that type of time is going to depend upon which type of flow stream you're talking about. So that's your flow, that's your step size relative to the average velocity. We can calculate n because n times these step size, these times the average velocity has to equal the length of the column. If you make n steps and each one takes time t and each one is at the average velocity u bar, that gets you out of the column. So that over u bar e t sub t, t sub t sub I. I now have n and I have L. put them together and I have my sigma squared. And I get my H by dividing by L. And this gives me my HETP. I'm going to knock off here. We're almost done. We're 90% done because these are easy. This is the key equation for eddy dispersion, for the A term. Right now, it looks like it has a dependence on velocity. But we'll get rid of that when we do the Van Deemter model. It'll disappear. Okay, see you Wednesday.